Okay, so we're going to continue with the central limit theorem today. We're going to look at more kind of problems and then kind of what happens with the variability as sample size gets bigger. So let's start with our first example. We assume that the actual weight of a certain candy bar, whose advertised weight is 2.13 ounces, varies according to a normal distribution with a mean of 2.2 ounces and a standard deviation of 0.04 ounces. So, what's the probability that an individual candy bar will weigh between 2.18 and 2.2 ounces? Again, this is a chapter 7 kind of question because you're only looking at an individual candy bar. So we're looking at the probability that we're between 2.18 and 2.22 ounces. So we know it's a normal distribution, so let's find our z-scores. So we're going to do 2.18 minus 2.2 divided by 0.04 less than z less than 2.22 minus 2.2 0.04. So 2.18 minus 2.2 divided by 0.04. We're finding the probability, between negative 0.5, 2.22 minus 2.2, and positive 0.5. So I'm going to use the formula sheet for this one, and then I'll use some of the calculator stuff later. So remember, when you're doing an in-between, we're going to find the probability that z is less than 0.5 first. It should be a less than sign. And then I'm going to subtract the negative. Because the formula sheet always gives you the less than. So I'm going to look at 0.5. So that's 0.6915. So 0.6915. Then I'm going to look at negative 0.5. Just on the other side. So negative 0.5 is 0.3085. So I'm going to subtract those. So I get a probability of 0.383. So now that's only if I picked one individual candy bar. Now let's suppose you plan to take a sample of 5 candy bars and calculate the sample mean weight. Calculate the probability that it's between 2.18 and 2.22 ounces. So now we're looking at a sampling distribution. So again, this is now a chapter 8 question because I have 5 candy bars. So off to the side, our mean stays 2.2, but our standard deviation is now going to be 0.04 divided by the square root of 5 because we're now taking 5 candy bars. So 0.018, we'll round. Now, it would be the same process. So now we're trying to find the probability 2.18 is less than x bar, because now we're looking at 5 candy bars, to 2.22 ounces. I'm going to use the calculator for this one just because you've seen the process up here. Again, it's totally up to you if you like to use the calculator versus the formula sheet. It's really up to you as an individual, just as long as you label your calculator stuff, you will still get full credit. So again, this is lower bound, upper bound, mean, standard deviation. Okay, so again, I have an 83, but when you get an 84 or a newer one, the prompts will come up. So second distribution, so 2.18, 2.22, 2.2, 0.018. So now my probability is 0.7335. Go around. Okay, so same question, but we went from 1 candy bar to 5. So how would you expect the probability to change if the sample size were 40 instead of 5? So if you look at from 1 to 5, it went up. So I would assume from 40 to 5, it would also go up. So we would expect the probability to increase or become closer to 1 as sample size increases, standard deviation decreases. Therefore, the probability will increase. Now, if you need a visual, I'm like a visual learner, so if I want a visual, think about, we're still looking at a normal distribution. So if n is 5, we sort of have a wider standard deviation. So if I'm looking like in between here and here, you're looking at the area under the curve. So you get about 38%. Now if I take a sample size of 40, what's going to happen, my standard deviation is going to get much smaller. So your bell curve becomes much taller. So the probability, the area under the curve, now becomes much more. So that's why it increases, because you're taking your normal distribution and making it, kind of shrinking it, making it smaller. So the area under the curve becomes more. Now this will change whether you're looking at the in-between, where we are in this problem, versus an outside, which we'll get to later. But for now it should increase. So now let's look at that. Now if I take a sample size of 40, is my assumption correct? So again, the mean here is going to stay 2.2, but our standard deviation is now going to be 0.04 divided by the square root of 40. So if I do that, I get an even much smaller number, 0.0063. So if I'm looking between 2.18 less than x bar, 2.22, again I'm going to use a calculator just for the sake of time. Normal, CDF, 2.18, 2.22, 2.2, 0.0063. Sorry, I sort of smushed that in there. So lower bound, upper bound, mean, standard deviation. So I'm going to go to normal CDF again. 2.18, 2.22, 2.2, 0.0063. And again, yours should come up as a prompt. So now look, our probability is 0.9985. So we went from a 38% chance with 1 candy bar to a 73% chance with 5, now a 99% chance with 40. So which one of your calculations above, this should say A, B, or D, would remain approximately correct even if the candy bar weights themselves had a skewed or non-normal distribution? So remember, that's the central limit theorem. So really the only one that works is part D, because we talked about yesterday the central limit theorem, you want n to be greater than 30. That means it's sufficiently large. So central limit theorem, which for the purposes of the second semester we usually always just put CLT, everybody knows it's central limit theorem, says if n is greater than 30, then the sampling distribution, because that's what we're working with in chapter 8, can be approximated by a normal distribution even if the population itself is non-normal. So really the only one that would work with would be D. A and B, we'd probably have to, our calculations would not be as accurate because we're only taking a sample of 1 or 5. So on the next page, let's look at a different question. So a lot of this is just examples. So Consider the population of American households that purchase holiday presents, and consider the variable the amount expected to be spent on holiday presents as reported in late November. Suppose that this population has a mean of 850 and a standard deviation of 250. If a random sample of 5 households is selected, is it valid to use the central limit theorem to describe the sampling distribution of the sample mean? No, since n is less than 30. Okay, again, you want n to be greater than 30 every time. So we don't know if this is a normal distribution or not. If you have a random sample of 500 households is selected, would the central limit theorem tell you the sampling distribution of the sample mean? Yes, since n is now greater than 30. So we should end up with a normal distribution no matter what. So with a random sample of 500 households, determine the probability the sample mean will fall between plus or minus $18.39 of the population mean. So between 831.61 and 868.39. So before you do this, off to the side, always figure out your mean of your sampling distribution. Here it stays 850, and find your new standard deviation. So we're going to have to take 250 divided by the square root of 500. And remember, this formula is on your formula sheet on the back of that first page right here. So if I take 250 divided by the square root of 500, 11.18. So I'm going to go ahead and do this one by hand. I did a couple calculator ones. So I want to find the probability 831.61 is less than x bar, less than 868.39. So actually I'm going to do this in the calculator. I always like the calculator for in between, because the lower bound upper bounds are really easy to figure out. We'll do a by hand one when we have a less than or a greater than. So 831.61, 868.39, 850, and then 11.18. And you can do that on the quiz or test if you want. Again, oops, that's mean. Let's get this mixed up. Just label. So, normal CDF, 831.61, 868.39, 850, 11.18. Oh, so it's like exactly 90%. So 90% chance that it falls between $18.39 within the mean, the population mean. Okay, let's try another one. The highway miles per gallon rating of a 1999 Volkswagen Passat was 31 miles per gallon. The fuel efficiency that one gets on an individual tank, that should be tankful, of gasoline would naturally vary from tankful to tankful. Suppose the miles per gallon calculations per tankful have a mean of 31 and a standard deviation of 3. Would it be surprising for a sample of 30 tankfuls to produce a sample mean that is less than 30.4 miles per gallon? So here's your N, and now we gotta figure out less than 30 miles per gallon. So off to the side, you know your mean of your sampling distribution is going to be 31. Your standard deviation, though, is going to be 3 divided by the square root of 30. So 0.548. And I would at least round to 2 decimal places. If you want to do 3 or 4, we kind of been working with 4 this whole year. Feel free. So we're looking at x bar is less than 30.4. So let's do this one by hand since we've been using the calculator a lot. So find your z-score. 30.4 minus 31 divided by 0.548. So we want the probability z is less than negative 1.09. And And the nice thing that with this one is it's already less than, so when I look it up in the table, I don't have to do 1 minus, because you only do 1 minus for greater. So negative 1.09 is 1379. So would this be surprising? If it's supposed to happen 13% of the time, I would say no. It's not surprising. You can kind of go with, there's no like, I don't know, rule in terms of being surprising or not, but I always tend to think 5%. If it happens less than 5% of the time and it happened in your sample, maybe something's wrong. That's kind of the rule I use. It doesn't necessarily have to work every time, but here, if it's supposed to happen 13% of the time and it shows up in yours, that's not too bad. Would it be surprising if a sample of 150 tankfuls then produced a sample mean less than 30.4 miles per gallon? So now we have a new sampling distribution. So the mean stays 31, but now our standard deviation, remember, is going to get much smaller. 3 divided by the square root of 150. So that 0.245. So now we're looking at the probability x bar is less than 30.4 again. So I'm going to do a new z-score. Z is less than 30.4 minus 31 over 0.245. So I want to look at the probability z is less than negative 2.45. So negative 2.4. 5.0071. So now, yeah, if it's only supposed to happen 0.7% of the time, and it happened in our sample, we're assuming we did everything right. So we say yes, because this would only happen less than 1% of the time. And you sort of assume you did everything right. So if it's only supposed to show up less than 1% of the time and it shows up, maybe something's wrong with their calculations. Okay, so our last example, sort of along the same lines. Assume a candy bar manufacturer advertises that a candy weighs 2.2 ounces. The candy bar weights vary according to a normal distribution, have a standard deviation of 0.04. Suppose you're skeptical of the manufacturer's claim that the mean is 2.2 ounces. So you take a random sample of 5 candy bars, weigh them, and find the sample mean weight of 2.15 ounces. Does this sample mean weight provide strong evidence to doubt the manufacturer's claim? So again, off to the side, we're assuming the mean's 2.2. Our standard deviation is going to be 0.04 divided by the square root of 5. So 0.018. So now let's look at the probability that I would get a mean of less than 2.15 ounces. So if I think about less than, we really want your candy to weigh more. So if I look at less than, that'll kind of give me a good probability. So I'm going to use a calculator. So normal CDF, I'm going to go negative infinity to 2.15. The mean's 2.2, and I have standard deviation 0.08. So lower bound, upper bound, mean, standard deviation. So, negative a bunch of 9s, 2.15, 2.2, 0.018. So I get a probability of 0.0027. So this is only supposed to happen less than 1% of the time again. So And if it happened in our claim, that means we should doubt what the manufacturer is saying. So yes, because this should happen only 0.27% of the time. And it happened in our sample. We then doubt the manufacturer's claim. And we'll get to more of this kind of as second semester goes on. That's kind of what we do second semester, is look at, okay, they claim something, what is it really supposed to happen or not? So, would finding a mean sample weight at 2.18 ounces provide strong enough evidence? So let's find the probability that X bar is less than 2.18 if we have our same sample size. So normal CDF again, negative infinity to 2.18 now. Same mean in standard deviation. So lower bound, upper bound, mean standard deviation. So, I'll show you the calculator, sorry. Negative, bunch of nines. 2.18, 2.15, oops, 0.018. So now, I did something wrong. Oh, I put the wrong mean in. That should be 2.2. Let's try that again. I'm like, wow, that's a high probability. 2.18, 2.2. I don't know where I got 2. Oh, it was the last one. There we go. There we go. So I get 0.1333. So now it's a 13% chance that it should show up. And that's not actually that bad. So, no. Since we should get a mean weight less than 2.18 ounces about 13% of the time. So the fact that it occurred in our sample doesn't make us doubt the claim. Okay, so because it went from 0.27% chance to 13% chance, it's really kind of a much bigger deal, so we're okay with that. So I hope you got a good idea of kind of what it takes. So a lot of it's the same as what we did in Chapter 7, except the only thing that's changing now is your standard deviation.